Hi there, and welcome to another, better play the titles for a bit longer, another exciting episode of Boombot V2. This is the final lesson before you move on to the cannon module. So we're actually going to set your robot up to fire the cannon module this time around. And thanks to user Canino on Thingiverse for sharing the Disc-o-matic cannon file. It's pretty good. All right, cue the Star Wars scroll. Right. Okay, that's it for special effects today. Here we go. The robot has a tether attached to it. It's down on the floor there and is zipping back and forth. And I'm controlling it with the joystick board right up here. So as I turn that joystick left and right, it turns. And as I do it slowly, it starts to whine and then it turns slowly. And just a minute, get straightened up right here. And when I push forward slowly, I'm holding it upside down. I should hold it upside right. When I push forward, it moves forward slowly. And when I pull backwards, it moves backwards slowly. So we're going to take a look at how we're going to be able to use the two potentiometers tucked right into your joystick right on here to make the robot move forwards and backwards. We're also going to take a look at using your control buttons because the control buttons right on your joystick here, you can see that one I've got hooked up to flash a headlight. That one's flashing the other headlight. And the third one is going to start firing your cannon and be able to blast little discs all the way across the room. Well, of course, I left the discs at work today, so I don't have them at home here. But anyways, that's what we're going to do, and that's what you're going to have your robot doing by the end of the day. You are going to be the most dangerous robot in your living room as you're able to whip around on the floor and fire that cannon and flash your headlights at people. Yay! All right, now that the fun stuff's over, let's get into the technical stuff. Before I delve too deep into the technical stuff, though, I do want to point out that when I started to record this episode, I was having a problem with the robot and it was not behaving properly. And when you're running into problems like that, a multimeter is going to be critical for solving your problems because sometimes that 9-volt battery is not putting out 9 volts. And that can be a problem for your circuit. So if you're running into problems, before you start panicking or doing anything else, take a moment and check that reading to make sure you're getting 9 volts off of your logic batteries. 8 will probably do the trick as well, but make sure that your batteries are charged up. And for my students, if you don't have a multimeter at home, remember that your DP scope has multimeter functions built into it. So plug that in, power that up, and look for the multimeter function under the top corner right there. So live batteries are important for making your robot work right. Okay, now that we've got your batteries all charged up and ready to go. Let's take a look at the joystick board and its schematic. Now you can see that there's space for a whole bunch of extra things to go onto the joystick board. In fact, there's header for an Arduino Uno to clip onto the back of it later on. There's space for an LCD display right in here or an I2C display. We haven't even talked about I2C yet, but we will. Down here, there's space for an ESP8266 or a Bluetooth connector, a power supply to come in from this side. So some output LEDs down here. Those are all things that are going to eventually allow you, should you so choose, to turn this, instead of being a tethered board, into being a wireless joystick board. And as I make this video, I haven't got the code figured out for that just yet, so I'm not going to talk about that at all. What I do want to point out is that in this section of the schematic, right down over here, this has everything that you need to get your joystick up and running. And what we've got on here is we've got the joystick set right in here. Okay, now the joystick is a dual axis potentiometer. And if you look right in here at this end of your joystick, when you move that up and down, you can see that this is just a potentiometer. And if I can get the light right on there, let's see if that brightens it up a little bit. You can see that that says B103 on it. Okay, so the 103 is it's kind of like a resistor color code. 1 and 0 are the first two digits, and the 3 tells you how many digits come after that. So 1, 0, followed by 3 zeros is 10,000 ohm potentiometer right on there. So when you're on one side right there, you're at the low end of the resistance, and you're on the other, you're at the high end of the resistance, depending where you're measuring from. And the middle pin, you can see we've got 3 pins down at the bottom, is what that sweeper in the middle is going to, and that's what's reading the voltage coming off there. So that potentiometer, as you move it forward and backward, gets electrically closer to one pin or the other. And you'll notice that your board is also labeled to say that on this side of the potentiometer, we have a plus 5 volt signal, and on this side we have ground. So this is going to be our y-axis right here, and that y-axis, as we turn it forwards and backwards, is going to vary between plus 5 volts and ground. If I pull it back this way, my little sweeper on the inside right here is going to be very close to the 5, so I'll be at 5 and I'll read 1023 on the Arduino. And when I push it forward, I'm going to be very close to the ground and I'll read closer to 0 on the Arduino. We also have another axis right in here, and you can see this has been labeled as the x-axis. And as we move that back and forth, when we push it over this way, we'll be close to the ground side. And when we move it over that way, we're close to the plus 5 side. There's another little thing right in here on the Arduino that you probably had a little bit of a hassle getting installed when we were soldering up the board, and that is a push button switch. So if you've played using any type of Ps2 style control console, this is what we call a Ps2 style joystick. And when you push down on that stick, there's a little lever and it comes over and it just pushes a little button right there, just like you've got on your joystick board. So since we already had one button up here, I added 3 more buttons to the schematic. And those buttons are hooked up with some resistors, just like on your main control board. And these buttons will be exactly the same as the buttons on your main control board in terms of their function. We have a header right on here that you can connect, and that header is going to take a plus 5 and a ground from your robot. So you've got plus 5 and ground coming up from the robot right here, and then it's going to return the, well, let's just pop that off, and you can see the header kind of covers it up, but you've got a plus 5 signal, an x-axis, a y-axis, and a ground. And then down here, we've got the switch button, which is going to go into analog pin A2. We'll take a look at that on the schematic in just half a second here. That goes on right there. I only had 6 conductor connectors, so if you ended up with a 6 conductor connector on here, we just leave the extra one blank. Let's see where all that sits on our schematic. It's down in this bottom corner that I've circled in red right here, and I'm just going to zoom in a little bit so we can take a closer look at what's going on down here. So this is my model for your joystick, and there's 2 potentiometers in here, one side on ground, one side on plus 5, one side also on ground, one side on plus 5, and the 2 outputs from that come back over here to, excuse me, to A0 and A1. Okay, now that's if you've got the wireless joystick hooked up. If that's for later on. What we're concerned about is that they come back right here, and here you can see that they come down here to your header going back to the robot. So that's this little thing right here, and that's running the voltage down in those wires right there. Here's where the power and ground will come in from your robot. So that's coming up from your robot right in here. And the final one is your button signal. And you can see this comes along and connects to all the buttons right here. So if you push on switch 2, for instance, so we've got a 5 volt signal coming down right here. So, sorry, the 5 volts, where's that coming in? Follow the 5 volt line right here. And we have Ah, there we go. It jumps over here. So here's your 5 volt, comes down right here, and the 5 volt connects to right here. So if you press the joystick button, this is the button built right into the joystick, then you'll get 5 volts going through there, and you will read a signal of 1023 coming out down there. However, if you don't push that button, there is a 5 volt signal that comes right here, and this is a series of voltage dividers. So each time you go through a resistor, the voltage gets a little bit lower because this is anchored to ground at the bottom, right over here. And each time you push a switch, then you get the voltage coming off there. And if you don't push any switches, this 100K resistor is just a pull down resistor to make sure this line sits at 0 volts no matter what else is happening. So really, to make this all work, you need 3 switches, a joystick, and 5 resistors. That's it. Oh, and the one header right here. Now, in the event that you have a different style of joystick, you can buy joysticks from Spark Fun and places like that, and you might have one of those sitting around in your shop. That's what this header that's unused on my board because I have just the joystick instead of the joystick board. But if you've got a joystick board from Spark Fun or something like that, hopefully your pinout will match with that header right there. And instead of using this joystick, you can use your joystick right in here. Okay, so that's some of the, excuse me, where's that mute button when I need it? Um, so that's some of what's going on the joystick board. Now that line comes all the way back down here and it tucks in the back of your robot and it plugs in to the exact same place on your robot that the line following board plugs in. And we've spent some time talking about the line following board. So you understand a little bit about what's going on there and you know it plugs into a couple of analog ports. You've got to unplug the line following board so that you can plug in your tether cable to your robot. We're going to use some of the same pins for doing that. Let's take a look at what that looks like on your main control board schematic. So here's the main control board schematic over here. And let's zoom in a little bit right here. It always zooms in so fast when I'm working on a 1080 screen, but here we go. So this was your edge detection board right in here. And the edge detector comes back and it uses a cable to connect to this header right here. Okay, and this cable H12 is what we call our joystick edge detector. And here's where you can see it ties into +5, and that carries the +5 to your edge detector board or up to your joystick board. Okay, and here's ground because of course you need common ground. And it's set up this way with the 4 pins, so it matches up with the 4 pins on the edge detector. We've added an extra one right here because you can see all the buttons on your main control board. The buttons tucked right in right here. There's those 1K resistors tucked alongside them right there. And this is forming a voltage divider right in here that works exactly the same as the voltage divider right on here. So the control board buttons, 1, 2, 3, and 4, work exactly the same as your buttons on here, 1, 2, 3, and 4. So if you program something to respond to these buttons, it will respond to these buttons the exact same way because they're the same thing, and they both come together and meet right there and travel into pin A2. Okay, so whenever we're reading buttons, whether it's on the main control board or on the joystick board, it's going to be an analog reading coming into pin A2. Now, when we hook up our X and Y axes, you'll see that they come in right here and they're on pins analog 0 and analog 1, which makes sense because we're already using analog 0 and 1 for the edge detection board. Keeping in mind that in order to plug this board in, you must unplug your edge detection board because there's no room for 2 things to plug in right here. Okay, so that's how this fits into your overall schematic. It's a fairly simple device. It's 2 potentiometers, and you've used potentiometers in lots of applications before, plus a voltage divider for the buttons, and we spent a lot of time talking about voltage dividers in the past. So let's take a look at how we actually use all of this to drive. Okay, so let's take a look at how we're going to make this work in code. Now, there's a couple of standard ways of driving the robot. And one of the ways is if you've got a two-axis joystick is to do what we call tank drive, where this joystick will control your right motor and this joystick controls the left motor. And you've got two single-axis controls. So if you want to drive forward, you push them both forward and both motors go forward and backwards, obviously. And then, when you go like that, you're able to turn. And that one provides the driver with a fair bit of control, but it requires two joysticks. And I'm cheap, so we built the board with one. So in your tank drive, you've got two single axis joysticks moving back and forth. And on our Arduino, we'd read 0 to 1023 up here as that moves forwards and backwards. And we'd have to map it out for our motor control because our drive routine goes from minus 255 to plus 255. So if you push it all the way forward, your 1023 should be sent to the motor as a plus 255. So basically, you can just divide that by 4. Um, Now, obviously, you can do a little bit more than that because you got a 512 right in the middle, and you don't want anything to be happening there. So what you do is you actually come in here and subtract 512 from everything. So this is minus 512, this is 0, and this is plus 512. Okay, and then you only have to divide by 2, and those numbers come right down here, and you're able to drive. So it's very straightforward to do a tank drive. Read this axis, okay, set it to neutral by subtracting 512 or whatever value you're sitting at right in here, and then just divide by 2, map it out to your drive command, and you're on your way. Do the same thing for the right-hand motor, and you're going great. And so if you've got two axes, tank drive works great. And if you're interested in doing something like that, there are ways to interface commercially made wireless joysticks to the Arduino. And so go ahead and Google wireless joystick in Arduino, and you can find that out a little beyond the scope of what we're doing right here. We've got just one joystick, and we want to be able to set it up so that when we push forward, the robot drives forward, pull backwards, it goes backwards, turn left, and turn right. Okay, and then we want little bits in here and stuff all in between. And for that, we have to use what's called arcade drive for the joystick. And so if you're doing any robotics competition, FIRST Robotics, VEX Robotics, you're going to see that there's different drive functions out there, and they're going to refer to them as tank or arcade. And we're going to use arcade. It's slightly more complex, but it's still pretty easy to do once you understand the tricks of what's going on. So before we get into the math behind it, let's just confirm some things that we're going to be talking about right here. Now on our board, we already took a look at it right here, and we said this is the y-axis. And on our board, because ground is up here, we're going to be 0 at this point and 1023 down here. And on our x-axis, okay, we're going to be at 0 when we're all the way over this way, because that's where it says ground right on there. We're going to be at 512 when we're in the middle, or pretty close to 512, and 1023 when we're all the way over here. Okay, and we call this one the x-axis. Now, there's no law saying you can't set your joystick up to drive this way or drive this way. However you want to drive, you can change your orientation around. If you want to be particularly unique and make sure that nobody else can drive your robot, you can set it up so that you're driving this way. You just have to play around with your mixing controls. Okay, now since we've got these numbers right on here, okay, there's a couple things we're going to do. And just as over here, I was saying we had to subtract 512 to set our neutral, so that this position right here, instead of reading 512, 512, okay, we can refer to this with like coordinates like you would on a graph. We want to set that to be 0, 0, so that's the origin. So when we take our thumb off, the robot's not moving, okay? So that's pretty easy to do because we can subtract 512 from each side. Now, the next thing we do on here that's not immediately apparent until you've worked with robots for a little bit is that we want to apply something called a deadband. Okay, now when you take your thumb off the joystick, you can see this, it's not always going to return exactly to 512, 512. Sometimes it might be 511, comma 513, or something like that. But the chances of it returning perfectly to 512, 512 are not really, well, it could happen, but it doesn't happen quite often. And so to save your batteries and keep energy from running through your motors and just to make life a little bit simpler, we're going to say that close enough is good enough. And this is what the deadband does. The deadband takes a range right in here. And if your joystick's reading in this range, say somewhere like 10 units above the 512 point or 10 units below, then it just says, you know what, make that they're trying to be at zero right in there. And you can expand or contract the deadband depending on the tolerances and precision of your joystick. So we'll see that the deadband shows up in our code. And basically what we've done now is we've come along and we've subtracted 512 from the middle. So this middle part is at 0, 0. We'll give it a deadband of about 10 on either side. So if it's within, when you take your reading, if you're right in here somewhere, this one will read a slight value in the x-axis because you're outside the deadband on the x, but you're still within the deadband on the y. So this will start your robot turning slowly to one side and not make it go forwards or backwards. Just gives you as the operator a little bit of tolerance as well. So for instance, if you push the joystick right up here and you want the robot to go straight, it will try to go straight because that is the same as pushing at 0. You don't have to be perfectly precise when you're inside your deadband. Now, on our joystick, we're going to refer to some of these positions with their readings right here. So this one is going to be at 0 in the x-axis. So I'm referring to everything as x comma y right here. Okay, and when I push this joystick forward, this is going to read 0 comma minus 512 right up here because when we were at neutral, it was reading 512 and I had to remap that, okay, so that we had 0 in the middle, positive 512 down here, and negative 512 right up there. Okay, I just subtracted 512 from whatever I'm reading right there. And now I get negative 512 here, positive 512 down here. And when I go to turn and slam the joystick over this way, okay, I'm going to read minus 512 in my x-axis and 0 in my y-axis. I go to turn this way and I'll get positive 512. Full backwards will be 0 comma plus 512. Different people, like I say, will have their joysticks oriented in different directions. For this robot, it makes sense to go this way, but you know what? If you oriented it differently, just flip your diagram around like that and your numbers will still work out. Okay, so that's what's happening with tank drive. Now the beauty of tank drive is that it takes a little bit of math to make it work. Very little bit. We're just adding and subtracting right here, but you need to think about this for a little bit so you can understand what it's doing and why it's doing. We want to take a look at our joystick coordinates, okay, and what we want our output to our motors to be. So if our joystick is sitting right here, straight up and down in the middle, then we want our motors to be at 0, 0 because your thumb is off the joystick and we want things to halt. Now, if I push the joystick straight forward like that, okay, my coordinates, based on the way this joystick is set up, is going to read 0, comma, minus 512. So 0 in the x, and 5 minus 512 in the y. So 0 comma minus 512. We want that to come out to forward, and we want our motors to be going at 255 comma 255. Okay, forward comma forward. And that's because we've got the drive routine set up in there that we're able to do this really easily. So everything we're doing is based on the drive routine that you did in an earlier lesson. Okay, so now we come down here and for full reverse, okay, it's going to read 0 comma plus 512 and we want these numbers to come out at minus 255, minus 255. If we slam it over this way, Okay, minus 512 comma 0 is going to turn left. So to turn left, we want the motors on the right-hand side going forward. So here's our motors on the right-hand side. They're going forward, and our motors on the left-hand side are going backwards, and our robot is turning left. And if we reverse that, then they're turning right. So 255 comma minus 255 turns us to the right. So we can take all of these numbers right here and we can come up with a formula that matches them together. Now, to go from the 512s down to the 255s, we're just going to divide by 2. Yes, I know it comes out to 256, but we'll take a look at the drive routine and talk about that in a minute. Okay, and so what we're going to do is we're going to take the negative of joy y, and then we're going to add joy x, and we're going to divide that by 2 to get our left motor reading. So just try this out on a couple of things right in here. Okay, well, obviously it works for halt because negative 0 plus 0 divided by 2 gives us 0. Okay, and keep in mind we're just looking at the left motor formula right here. So for full forward, in our x-axis, we're at 0 right now, negative 512. So negative of negative 512 is positive 512, okay, plus 0 gives me 512. Divide that by 2, and our left motor reading comes out at 255. Let's test this formula for our right motor. Now, our right motor, instead of adding the y-axis, we subtract the x-axis. Okay, so in here, it doesn't make a difference because the x-axis is 0, so we're subtracting 0. We've got negative 512 in here. Negative of negative 512 is positive 512. So 512 divided by 2 is 255. So this gives us our 255 and our 255 for going forward. Let's try a turning one right in here. Okay, you can try a couple of these on your own. So for turn left, right over here, we are going to be at negative 512 comma 0, and we want this side to be going backwards and the right side to be going forward. So take a look right in here. Our left motor is at negative 512, so negative of negative 512 is positive 512, okay? And then we're going to add in the sorry, this is our x-axis right over here. So oops, now I'm getting myself confused. Let's start over. This number right down here as negative 512 in the x-axis, that comes in here. So we're going to add negative 512. There's no negative in there. We don't flip it around. So this comes out as negative 512 for our left motor. And down here, the y-axis is 0. So 0 plus negative 512 divided by 2 gives me negative 255. Pretty close. Okay. Then for our right-hand motor, we want that to be a positive number. Well, we're subtracting negative 512 in here, okay, because we had negative 512. Minus of minus 512 is positive 512. This number's sitting in here at 0, so positive 512 divided by 2 gives us 255 right in there. So you can work through the different combinations and permutations. And basically, you'll get a map of how you want your robot to drive using these formulas right in here. Now, again, depending on the orientation, you use a different joystick. It might be positive joy Y minus joy X to get your left motor, or it could be negative, but it's always going to be some format of this, just adding the two together. There are more advanced versions of this that get into exponential mapping so that a small movement of the joystick has either a lesser or greater impact than a large movement of the joystick. And you can sometimes get finer control on there or better map it to your robot performance. You don't need to for our robot. But just so you know that there are other mapping formulas that instead of just being a linear mapping formula are more advanced. You don't need to know about them. They're all just derived from this general concept that you're mixing an x-axis and a y-axis to get a left motor and a right motor reading. Now you will run into some situations where you want to go forward and turn. So for instance, when your joystick is cranked up this way, So it's not just up here, it's not just up here, but you're pushing off at a 45-degree angle. And let's take a look at the situation where you're at minus 363 and minus 363, okay? So you're over on this side right here. And when you add that together, so in your first formula right here, you get minus 363 plus minus 363. Um, there's your formula right in there, and divide that by 2. You end up getting a output of 0 and 726. You divide that by 2, and you get 0 and 363. And our motors can't travel at a speed of 363. But you'll recall in our drive routine, back when we were talking about the drive routine, we had a little check in there to make sure that we didn't go beyond 255. And at the time, I didn't make too much of a fuss about it. I just said that there was a possibility that you'd get some bad data later on. Well, we'll go back and we'll take a look at that, because trying to send a command of 363 is not going to work out well, because the biggest number you can send is 255, but our code catches that and sets our motor full speed anyway. So this is going to result in one motor parked and the other motor turning forward. So instead of turning like this, now you're going to turn like that. So slightly different changes in how your motor responds, and it actually behaves really naturally. Now, if you let go of the joystick and it tries to return to 0, 0, but it doesn't quite make it, and you're at -5 and +5, well, we still want your robot to stop. So this is why we use the deadband, okay? And we do a little check to see if you're close to 0, and before we do any of the rest of this math, we do the deadband stuff. And so if you're at +5 and -5, we just map that out to 0, 0. And if you're down in the bottom corner, again, you can go through and you can do the math right on here, and you come up with commands for your motors, and you apply some limits to it, and it stops right there. So the key takeaway from this is to look up the joystick arcade mapping. And that's, for our robot, is this formula right in here, okay? And in the future, if you can't remember that exact formula, or you need a bit of help finding it, it's going to be a little bit different depending on how you want to map the numbers out exactly. But the keywords that you search for: arcade, mapping, and you might add for robot. Okay, and that's really easy to do. It applies to FIRST Robotics, it applies to VEX Robotics, it applies to just about every type of mobile robot that you've got. And that's because we've got two main types of drive: tank drive and arcade drive. Okay, so let's go and take a look at how we implement this in our code. All right, so in our code right here, we've got some things that we already need installed right in the code. We've already set up a button pin for reading the buttons so that you can come along and push those buttons back and forth. And the reason we have it there is because that's the same thing as we used in our very first exercise for reading the buttons on the control board. Now, for our joystick, we're going to add a few functions right in here. Okay, and or functions. We don't actually have a function built up for this, although we could build one. We've got a few variables and a couple constants. So our constants right here, for our board, the X pin is going to be attached to pin A0, and the joystick's Y pin is going to be attached to pin A1. And those, like I said, are also the same ones used for the edge detection board, but because you can only plug one thing at a time into the header, you're going to have made a physical hardware choice on whether you're running using the joystick board or the edge detector board. Okay, the count variable's been sitting around for a while. I don't think we really need that in there, but this is two variables, however, that we do need: joy X and joy Y. This is when we do the analog read of the value on these pins. is where we're going to store that value so we can do our math to it. And finally, we've got a button variable so that we can read the buttons. And when we read the buttons, we're going to divide that number by 240, just like it says right up here, and that'll tell us which button is being pressed. Okay, everything else is pretty much the same. We've got left motor, right motor. You can ignore this right here. We'll use that later on when we're using these concepts to drive your robot from your cell phone. And then we're just going to come down here. I don't think we have to configure anything new. We're going to come right down to void loop, and we're going to take a look at how our code works out in void loop. Okay, so the first thing that we're going to do is we are going to read the joystick's X pin. And so when we read this value right in here, we know that our X pin is the one going from side to side right in here. And we want to apply a deadband to it. And so right in here, I've applied a deadband of 20 units. So the first thing it does is it reads this, it subtracts the 512 because like we said, in our default situation, you start with this number being 512, but we want to shift everything 512 units over. So instead of going from 0 to 1023, we go from minus 512 to plus 512 and have 0 in the middle. The deadband right here means that if we're close to being at 0, we automatically set it to 0. So it's just a quick little check, and if we're in this gray area right up and down here, we just set it to 0, and that's our deadband. And we do the same thing for our y-axis, which is on our joystick, the forwards and backwards. Okay, and again, you can tweak the deadband values around in here so that you can play with it. On this stick, I find 20 is probably overkill. You could probably get away with 10. On a less precise stick that doesn't center by itself as well, you might need a bigger value. All right, and then we read our button. Okay, so button tells us which button is going to be pressed. And interestingly, it works out really nicely that you can just do an analog read of your button pin, divide that value by 240, and it tells you which of the 4 buttons is being pressed. And if that answer comes up as 0, then no button is being pressed because you've got 0 volts coming in, and 0 divided by 4 is still 0. All right, now I've got some print routines right in here so that you can read what we're getting coming off of the joystick. Okay, so when you've got your robot set up and plugged into here, just gonna plug that in. And you can see when we're running off the USB, we don't need any external power. We're not draining our 9-volt. So let's go ahead and turn on our serial monitor and see what data we're getting off of the robot. Takes a second for that to boot up as the robot boots up there. Okay, so here is data that's going to stream in from our robot. And it's got our x-axis, our y-axis, our button condition, okay, and what we're going to output to our left motor and to our right motor. So, out of my way there, robot. Let's take a look at the control board. I'll hold it the right way around right here. Okay, and let's just take a look at the buttons right here. So if I push this first button off over here, you'll see that button, its raw reading is 251. If I divide that by 240 using an integer operation, I'm going to get 1 as an answer. If I divide 500 by 240, I'll get 2. And again, it's integers, so there won't be any fractions on there. Push this button, divide that by 240, I'll get 3. And divide this button by 240, and I'll get 4. Okay. Yes, I could use the full 255 value, but you can see sometimes there's little bits of fluctuation in there. I got a 499 in there, a 250 right flashed up right in there. So I just leave myself a little bit of room, and that's how we're going to read our buttons right in there. We just go, okay, which button's being pressed, divide it by 240, and we've got our data. Let's take a look at the joystick. If I push the joystick all the way forward, okay, My y-axis goes to 512. And you can see now that my motors both map out to 256, 256. Those numbers aren't good for our drive routine, but we'll take a look and we'll remember that our drive routine does have error catching right at the beginning of it to make sure that we don't put impossible values into the drive routine. If I pull backwards on here, okay, now see my joystick doesn't quite go to 512 all the way back. It comes down to 511, which is pretty good. And you can see my left and right values come to minus 255, which is just perfect right on there. And if I turn to the left, then my right motor is going forward and my left motor is going backwards. And because I've got a math function in here making this happen, once I get out of the deadband, I can make all of these numbers come together, and they're nice little numbers that work right through there. And so you get fine and precise control of your robot. So if you run a serial monitor using this code, this can help you troubleshoot any problems. And you'll notice that because of my deadband, every time I let go of this, it returns to exactly 0, 0, even if the joystick is off by a tiny little fraction. And in fact, in order to make your robot move, you need to move your joystick enough to let it know that you want to be going somewhere. You can see right there that if I back off right there, I come down 90, 80, 70, and I can get some readings in the 20s, but I can't get anything less than that. So a tiny little touch or an accidental bump isn't going to cause you any problems because we've got that deadband. Alrighty, so that's what's happening right there. We're just printing out that data so that you can see what's going on. This is where the rubber hits the road right in here. And these are our two big calculations where we say, I want my left motor to be this formula right here. Now, these formulas are the exact same as the formulas that we spelled out right in here on our notes. Okay, and our right motor to be right in here. And then we print out that data, and you saw that data coming out. That's really useful for troubleshooting. Okay, feel free to use serial print statements. If you don't want the serial print statements, you can always delete those statements later on, or what I like to do is /* and */. Oh, I've got a */ right in here where I talk about commenting things out. I better /*, there we go. So you can comment your code out right in here. Okay, and if I get rid of that, there we go. And you saw everything go nice and gray. You can also come in and you can just put // at the beginning of every line, and the computer won't compile that for you because it's all grayed out right now. So if you want to save that for troubleshooting later on, you can, and that's called commenting out your code, and it's pretty useful. Just lets you leave the code there, but have it not execute when the program runs. And you can do the same down and comment that all out. Alrighty, so after we've done our arcade mixing on the joystick, yeah, don't comment these ones out. That's your arcade mixing right in there. That's the critical aspect of driving with your joystick. Then you're going to execute the drive function. And the drive function will jump you right down here to the void drive function that we wrote earlier. And you'll remember that the left speed and the right speed get passed in here from whatever called the function. And the first thing it does is it checks to see if the left speed, so remember we said we were going to get some values that might be like 300 or something and don't make any sense. And we're going to say that if a left speed is greater than our maximum forward speed, then our left speed is going to be equal to our forward speed. So we're just taking a look and we're saying, okay, the fastest we can go is 255. If somebody asks us to go 360, we just bring that down to 255. And the same thing in reverse. If somebody asks for minus 360, we're like, fastest we can go is minus 255, and we stop right there. So those error checking routines that we built in back in our very first, I guess, second episode on here are going to come in really useful right here because they're going to filter out bad data. Okay, everything else in the drive routine is exactly the same. So remember, if this isn't working on your robot, you may have to double check to make sure that the motor left reversed and the motor right reversed constants are set up for your robot based on how you've wired your motor into your robot. Okay, um, that honestly is about it for the driving. Now, I've got a few if statements right in here, okay, and a couple of these are pretty simple. So if button is exactly equal to 1, then we'll digital right LED left high. Otherwise, we'll digital right LED left low. So we've got control of one of the headlights. If button equals 2, then we'll turn on the other headlight, turn it off if it's not pressed. And finally, if button equals 3, then we will digital right motor 3 comma high. And motor 3 is where the action is because when you turn motor 3 on, let me make sure I've got some power right here. And where's my, when you hit motor 3 right up here starts up and starts firing little discs that you've stacked up in here all around the room. And that is going to be awesome. And as soon as you finish this episode and upload the video of your robot driving around with a joystick, you're going to be eligible for a Canon upgrade, and you're going to have Motor 3 running on your robot and firing things. So let's just take a quick look at what Motor 3 does. We did have to add, as you can probably guess, a couple of commands in here. Remember, very important in your setup routine to set the pin that we call Motor 3 to be the output. And up in your declarations and definitions, if we haven't done it already, that we've set Motor 3 to be pin 11. Okay, so make sure that you've got those set in there. And if you take a look at the schematic, okay, and we drag this down over here, motor 3's up in this corner right here. And here's pin 11. Okay, pin 11 comes out right over here from your Arduino and comes right up here, right along over here, and it comes through a resistor in right here, a 1K resistor, so that we're not trying to run the motor using motor 3, and it turns on an NPN transistor. Now on your board, that NPN transistor, oh, I don't have this opened up, it's the TO220 package sitting right down in here with those 3 legs coming up there. That's the big transistor. TO220 is what we call any device that's shaped like that. Our more standard transistor shape is what we call a TO92. Okay, so it's a TO220 format transistor, but honestly, any NPN transistor should work right in here. And what we've got is we've got our motor power signal coming down right in here, coming right to here. And this is the header that comes up to our motor. So you'll see that there's a wire that comes down right inside here, and that wire plugs in right down inside right there, okay? Now, that wire is going to be, one side of it will be at our motor voltage, and the other side right here is going to want to go to ground. But the only way it can get to ground is to go through this tip 120 transistor, or like I say, any NPN transistor that fits in the holes will work. So in order for it to get to ground, we need to set this signal to high. That turns the NPN transistor to on, and electricity will come up here through your motor. It'll come back down on this side to ground, and your motor will spin. Now, unlike our H-bridge motor control, we do not have directional control of this because we've only got one pin going here. So one pin can be either on or off, and we can only tell the motor to go
on or off. So in order to get the cannon working right, you do have to wire you do have to wire this motor up in the correct orientation. But thankfully, because it is exposed right here and it's easy to get at, and this little header right here is down exposed and easy to get at, when you're hooking things up, it is fairly easy for you to come along and swap that direction in the event that your motor's not swap that direction around. Just resolder that or recrimp your connector if your motor's spinning in the wrong direction. We have a protection diode right in here because the motors are an inductive device. And sometimes when you start and stop inductive devices, they will put voltage spikes or giant voltage sucks into the system, and they will be such high voltages that they can draw voltage backwards through the transistor, destroying it. So in the event that we get a little bit of negative voltage coming through right here, the batteries will absorb it on this end, and current can just bypass the transistor through the diode. So if we get little voltage spikes across there big enough to damage the transistor, we've got a diode that just says, oh yeah, whatever, have your little bit of current, and it can go back right there. Obviously, the current can't come through that way. It has to pass through the transistor when heading in this direction, but you just don't want to ever have a transistor that has too much reverse voltage put across it. So you protect the transistor by putting a little diode right in there. That's about it to get your, oh, I guess it works better if the battery's turned on, to get your Canon up and firing. So the Canon, like I say, is a file that's on Thingiverse. It's called the Disc-o-matic. It's been shared by the user named Canino on there. I think there might be some hacks and modifications that somebody who has some time to sit down with Fusion might want to do, but it's a neat design and we appreciate it being shared, and it was actually part of the inspiration for this particular robot design. Um, there's a couple of mods and hacks that we make when we do put it together. In Canino's instructions, they say to glue this motor in. I find if you countersink right in here, I think that's a 630, no, maybe it's a little 440 flathead screw, actually allows you to change the motor in the event that you have a problem with the motor. And you can see I've got a red slidey thing right in here, so you can see that sliding in relation to the black. If you print one out in a solid color and swap your moving part with another student's moving part, then you're going to have a neat looking robot. And you can swap whatever colored parts you want to make your cannon look really good. So anyway, upload the video of your robot driving around and upload your drive code, and you'll be good to go and ready for your cannon upgrade. Moving on to the next level.